exponential and logarithmic functions. Section 4.1, exponential functions and their graphs. So first, let's recall power functions. So f of x is a power function if we have some variable x to some fixed exponent. So an example would be f of x equaling x to the fifth power. So 5 here is some fixed number, and the variable x is in the base. So I have a variable base. Well, an exponential function will be very similar to this, but rather than having a fixed exponent, we'll have a variable exponent. So f of x equaling 5 to the x is an example of an exponential function, because my exponent is a variable and my base is fixed. A logarithmic function. Well, the inverse of an exponential function will be a logarithmic function. So let me give you an intuitive idea of that first. So ln of x, this will stand for the natural logarithm of x, will be defined as the area between the t-axis and the graph of 1 over x for t between 1 and x, where x here is some positive value. So ln of x is just this area here that I shaded. Another way of thinking of this is if I define a function e to the x, then the inverse function of this exponential function will be ln x. We can then define the exponential function with base b, where b here is greater than 0 and not equal to 1, as b to the x is just e to the b ln x. Okay, so let me give you some intuitive idea about this. So the exponential function with base b, where b here is greater than 0 and not equal to 1, will look something like this. So long as b is greater than 1, it'll always be increasing concave up. It will have no vertical asymptote, but it will have a horizontal asymptote, being the x-axis, y equaling 0. It has no x-intercept, a y-intercept at 1. If b is greater than 1, well, we'll be calling this exponential growth. And so let's write exponential growth as follows. A, some amount, is equal to a sub 0, the initial amount, to the kt, where k here is called the growth constant. And if k is greater than 0, then we will call this, this will be exponential growth. And then t is, well, time. So examples of things that exhibit exponential growth, well, population. Well, this would be an example of a population growth, or money, interest. So recall the simple interest formula, A equaling P times 1 plus RT. So in this case, A sub 0 is just P, K is just ln of 1 plus R. Compound interest. So rather than just giving your interest all at one time, at the end of one period, what we'll do is we will give you a portion of your interest divided up into equal subintervals of your period. And so suppose I will compound this n times over a period. Usually the period is per annum, annually, per year. And so n is the number, usually the number of compound periods per year. It doesn't necessarily have to be, but that's many times that's what we define it as. R here is the interest rate per annum. Again, this is usually done in years. And so A is equal to P times 1 plus R over N, all to the power NT. Again, this is exponential growth. A sub 0 is just P. K here is N, ln 1 plus R over N. Continuously compounded interest. So suppose that rather than compounding this n times per annum, you do it an infinite number of times per year. Then we say that this is continuously compounded. And while the formula is just A equals P e to the RT. So again, while here it's exponential growth. A sub 0 is P and K is R. So as before, A is the amount that you have in your particular investment. P is the amount that you invest initially, the principal. E is, well, a constant, that Euler's constant. R is the interest rate per annum, let's say, and T is the number of years. Exponential decay. A equals A sub 0 e to the minus lambda t, where lambda here is greater than 0, called the decay constant. So if I have y equaling b to the x, let's say, where b is between 0 and 1, then it exhibits exponential decay. It is always decreasing, concave up. It has no asymptote of the x-axis, y equaling 0. There are no x-intercepts, but there's a y-intercept at 1. Things that exhibit exponential decay, well, radioactive decay is the usual model that we give. So let's do some examples. Oh, wait. Oh, I see. We did that first part. So let me do on page 425, problem number 20. Simplify each expression. And so I have 5 to the radical 2 to the power radical 2. So let's try to simplify this. So this is just equal to 5 to the power. Well, if you have a base to an exponent, you just multiply exponents. Rad 2 times rad 2 is just 2, and 5 squared is 25. Let me do my next problem. Problem number 22. A to the rad 12 times A to the rad 3. Well, if you have the same base, then you add exponents. So I'll add rad 12 plus rad 3. Well, the way I've written it, I can't simplify it yet, but I can simplify rad 12. Let's write 12 as 4 times 3. The square root of 4 is 2. And so now I have like radicals. So now I can add 2 rad 3 plus 1 rad 3 is 3 rad 3. And that is your answer. Okay. Find, actually I can move this up just slightly. Find f at 0, f at 2 for each of the given exponential functions. So let's do that. F of x is equal to 4 to the negative x. Let's determine f at 0 is just 4 to the negative 0. Well, negative 0 is just 0. A non-zero base to the exponent 0 is just 1. So f of 0 is 1. Let's plug in 2. So f at 2 is 4 to the negative 2. Well, let me rewrite this as, since I have a negative exponent, let's write this as 1 over, take the reciprocal. So remember, a negative exponent means take the reciprocal. So 1 over 4 squared. And so f at 2, 4 squared is 16, is 1 over 16. Let me do problem 30. Graph each exponential function. Well, the base here is less than 1. Therefore, it looks like exponential decay. And the graph should look something like what we've written above. So it decays, looking something like this. Y equaling 1 over 3 to the x. It intersects the x-axis, the y-axis at 1. It is always decreasing, concave up. So at 0, it's 1. At 1, it's 1/9. 3, it's 1 over 27. At negative 1, it's 3. At negative 2, it's 9. And so it looks something like this. Let me do the next problem. Problem number 56. So in problem 56, graph each function by using transformations. Do not use a graphing calculator. Okay, so let's replace f of x by y. And so this looks like a translation of y equaling 2 to the x, where I've replaced x here by x plus 3. Since we're adding 3, that means I'll be going in the negative x direction 3 units. So I'm going to translate this by 3 units to the left. Okay, so maybe I'll try to put it here. So first, let's sketch the graph of 2 to the x. And so the graph of 2 to the x should look something like this. So this is a graph of y equaling 2 to the x. It goes through 1. The y-intercept is at 1. And it's always it has a horizontal asymptote of y equals 0. So now let's move this 3 units to the left. Okay, so this is going to go 3 units here to the left. Oh, actually, maybe I'll sort of do that. Well, okay, so let's just copy this and see if I can move it. Oh, it doesn't do that. Okay, wait. See if there's a way to copy this. Oh, it doesn't let me copy it. Okay, so all I'm going to do is I'm going to move this guy 3 units. So I'm going to take this and move it. Of course, now it doesn't. It's going to move both of them. Wouldn't you know that? Okay. Okay, it doesn't matter. So I'm going to move this 3 units. Doesn't look that good. 3 units to the left. Okay, so it looks something like that. Actually, let's see if I can just move it down. Of course I can't. Okay, good enough. So that's the graph of y equaling 2 to the power x plus. So I've just taken this and moved it 3 units to the left. Let me do problem number 81. In exercises 81 through 84. Yes, question.
I have a question on previous. What is the I'm not understanding why the 2x, what does the 2 represent?
Oh, okay. So if I look here, let's plug in. It's just how fast this grows. So the shape will look. Say if I plug 1, it's at 2. So if I look here at 1, this. Well, let's see here. Wait. This is going to be at 2. Okay, then at 2 will be at 4. So that tells you how fast this goes up. Okay, now if it was 3 to the x, then it would just be a little bit steeper. At 1, it'd go up at 3, so it would just look a little steeper. If it was 10 to the x, it would go up even faster. So that base there tells you how steep it looks. So, 2 to the x looks something like this. 10 to the x would look like this. 100 to the x would look like that. So it just tells you So this is like 100 to the x, 10 to the x, 2 to the x. Okay? So
Okay.
those give you sort of the relative speed at which they're growing, they're increasing. Okay?
Okay. And the x on top of for the exponent of 2, does that mean that the x represent the y-intercept at 1?
So this x up here
Mm-hmm.
is the variable. So that's the, in other words, like here, I would plug in 1 here, and that's 2 to the 1, so that gives you a 2. And if you plug in a 2, then that says, well, 2 squared is 4. Okay? So you're just plugging in x's here. So if I plugged in like a -3 here, actually now let's do it in black. Then this guy moves 3 units over. Okay? So then at -2, you're at 2.
Okay.
Okay? So what you've done is you just keep moving this guy here. You move this guy by 3, this guy by 3, this guy by 3, etc. You're just moving this whole graph over by 3. But you could plug in, say, a -3 here. -3 plus 3 is 0, so 2 to the 0 is 1. -2 plus 3 is 1, so 2 to the 1 is 2, etc.
Okay.
Okay?
Thank you.
Okay then. In exercises 81 through 84, assume that there are no deposits or withdrawals. Compound interest. Initial deposit, I'm using red. Go back to black. Initial deposit of $10,000 earns 8%. I'll write this in decimal. Let me get another page. Oops. Here's the new page here. Okay, 8% interest compounded quarterly. So there are 4 compound periods. This is obviously in dollars. And this is per annum, per year. And this is 4 compound periods per year. Since it says that it's compounded quarterly. How much will be in the account in 10 years? So you want to figure out the amount that you have in the account after 10 years.
Excuse me?
Let's use the
Hello?
compound interest formula. Yes.
Oh, I'm sorry. How did you get 4?
Oh, because it is quarterly. There are 4 quarters in a year.
4 quarters in a year. Okay, sorry. Thank you.
Yeah, since it says quarterly.
Okay.
Okay, so the compound interest formula is just P 1 plus R over N. My R's and N look the same. Over R over N to the NT. Okay, so let's plug in the above data into this formula. And so A, the amount, A, equals the principal, which was 10,000, 1 plus R, which was 0.08, over N, which was 4, to the power N, which was 4, and the number of years was, I forgot. Oh, 10 years. T was 10. It's right there. Okay, so A equals 10,000. 0.08 divided by 4 is 2, 0.02. And so 1.02, 4 times 10 is 40. And so that's the amount. But usually we don't give that in that form. We multiply it out. So let's plug that into our calculator. In our calculator, it gives 220,080.4. And so let's round to the nearest penny, 22,080.40. So usually that's the form that we like to give this in dollars to the nearest penny. Okay. Let me do problem number 95. Saving for college. In 20 years, a father wants to accumulate $40,000. So in 20 years, a father wants to accumulate $40,000 to pay for his daughter's college expenses. If again, I'll write this as a decimal, and this is per annum, per year. And again, it's compounded quarterly. So since it's compounded quarterly, there are 4 quarters in a year. So 4 compound periods per year. So 4 compound periods per year. Okay. How much must he invest now? So they're asking how much he must invest. What is P? Okay, so let's do this. So I have, again, the compound interest formula. A equals P1 plus R over N to the NT. Okay, so the amount is 40,000. Oops, 40,000. 40,000, 1 plus R, 0.06 over N, 4. Was it 20 years? And then T was 20. Okay, so let's simplify this. Oops, I put that in the wrong place, didn't I? Oh, that's an error. I'm sorry. 40,000 is equal to P. Sorry. We want that the amount that you have at the end of 20 years to be 40,000. Okay, so I have that 40,000 is equal to P. 0.06 divided by 4 is 0.015. And so this is 1.015 to the power 4 times 20 is 80. And so P is equal to, divide both sides of your equation by 1.015 to the power 80. So that's your answer. But again, we don't like that sort of answer. So let's plug this into our calculator. And so P is approximately 12155.6059. And so this is approximately $12,155.61. So that's how much you should invest so that in 20 years you have $40,000.